One Thrasher here. We are looking at Newton's second law. We're going to start with the definition, and then we're going to, over the next couple videos, apply it, because while it starts off as a fairly straightforward equation more than anything else, it is very fundamental in describing how, why, and if objects are moving. So we'll be building off of this law, the second law, a lot over the rest of these videos and this course. We will also spend a little time looking at some types of forces, because that will be important when it comes to applying this second law. So first, the definition. If you remember, the first law from Newton is all about what's going on if there's not a net force. If something is not pushing or shoving or tugging or throwing an object, what the first law tells us is that that object will do whatever it was doing. If something is at rest and there's no net force, it will stay at rest. If something is moving, it will keep on moving if there's no net force. So the second law from Newton, it follows pretty obviously. Well, what if there is a net force? Let's see what's going on if an unbalanced push or pull or tug is applied on an object, and what happens if there is a net force? The object's motion changes. All right, we learned about acceleration. If there is a net force, an object might speed up, it might slow down. If it started off not moving, it may begin moving, it should begin moving. It could also include changing the direction of an object. So when there's a net force, the motion of an object changes. That object has to accelerate. All right, well, that certainly just sounds like an equation, and here's the equation for Newton's second law. The acceleration, A for acceleration, is equal to, this here is uppercase letter sigma, Greek letter sigma. Okay, if you know math, it represents the sum of. This here is net force. That's helpful. All right, the net force of the object. If you think of it in terms of summation, it's like you add up all the forces. You take the net, the total force. So here I have the net force, and I have here the mass of the object. So acceleration, well, you'll accelerate more if there's more force. This is in the numerator. That probably makes sense. Bigger shove means something is going to accelerate more. And you'll accelerate less if something has more and more and more mass. So that should also make sense. Me pushing on a pencil versus me pushing on a train, well, the pencil will probably move more, should move more, with the same force, because a pencil is much less mass. Okay, so here's Newton's second law describing an object's acceleration. While this equation is obviously valid, we're most often going to utilize it in this form. It's the same equation. All I've done was solve for net force on the left. This is going to be convenient when we are looking at all the different forces that are acting on objects. So same equation, same idea. All right, this one is just going to be a little more convenient. It's the more often seen equation. Okay, the only other thing I want to add is that the unit for forces, because I don't think we've written it down prior, all forces are measured in things called newtons. Pound is another unit of force, but it's not the one we're going to use in class. The SI unit for force is newtons, abbreviated uppercase N. And if you think about it, here this net force, which is in newtons, it must be the same unit as whatever my equation is. This is kilograms. This is meters per second squared. So a newton is equal to a kilogram meter per second squared. That's not super important. All forces, though, are measured in newtons. We will be elaborating on this second law a lot over the next coming videos and class. So let's move on to part B. If we want to look at the forces acting on objects, we got to make sure we know some basic types of forces. So that's what part B is all about, just going over some common forces, their symbols. Some of these might have an equation, and then we'll be utilizing them later. So the most common force you might be aware of when you think of forces is weight. We often abbreviate weight as uppercase W, or you might see forces with subscripts, F for force, and then since weight starts with a W, a subscript of W. You could use either one. I tend to use this one a little more often just because I'm lazy and I only have to write down one letter, but a textbook might use this, College Board might use this, okay, but you could use either one. They mean the same thing. Weight is simply the downward force. It always acts downward, a downward force on objects due to the gravitational pull from the Earth. Any object here on Earth feels the force of weight. The equation, you should write this down, it's equal to mg, super straightforward. This is the mass of the object. And g is that same g we saw before, 9.8 meters per second squared. So the weight, you just take the object's mass in kilograms, remember, you multiply that by 9.8. There's weight. Next force is the normal force, and this one's a little weird. Think of right now something that's sitting on maybe the table you're at, or maybe you're at a desk. Maybe you have a computer at the desk, maybe you have a cup of coffee at the desk, maybe you have your calculator or a pencil or your notebook. If you look at that object that's sitting on the table or sitting on the desk, you might think, well, we know there's weight acting on it. Why isn't that cup of coffee falling through the table? And that's kind of a silly question. You could probably reason, no, the table itself is applying a force. All right? A support force is exerted on objects when they're sitting on something. If you're standing on the floor is providing some support. You're obviously not falling through the floor. The floor is exerting an upward force. Just like the table is maybe applying an upward force on your computer. Okay, maybe a desk is applying an upward force on your pencil. A support force from some surface. Okay, floor, table, ramp, etc. Okay, so the normal force is referring to a support force. The reason they call it the normal force, usually abbreviated as N or, oops, this should say or right here, yikes, or, again, F with a little subscript of N. This force is always acting on the object at an angle that's perpendicular, normal, to the surface. So here I have my table, like here's a table right here. I don't know, maybe this is a book or something, this thing in yellow. There's a normal force. If we extended this normal force, oh gosh, can't draw straight lines, it is perpendicular, 90 degrees to that surface, to the table. That's why it's called normal force. Now, a little trick here. Let's say I take that book and I put it on a ramp. All right, weight always acts straight down in this example, straight down in this example. The normal force, the rule is it's always perpendicular. So here I have it drawn. Again, if we extended that line, perpendicular, if I try and draw my little geometry symbol for perpendicular to here. Here's the surface of the ramp. Or maybe you have like a driveway in front of your house or apartment and it's like sloped. Maybe this is the driveway and here's your car. The normal force is always perpendicular. Okay? That's normal force. Tension, really the last official force we're going to talk about in this video. Tension is really just the name we give to forces acting on objects from things like a string or a cable. Maybe it's a chain, rope, twine, things I like to call danglers. You can dangle a string in front of you. You can dangle a piece of rope. All right, so it's really just a name given when things are being tugged on or supported from these different types of string-like objects. Okay, really tension and these strings or these cables, they act kind of like extension cords. The force is transmitted through that string. All right, this person here could just use their arms and pull the box, but they could also lash a rope around it and tug on the string. Maybe if they had a really long string, they could tug on it from, oh man, can't draw, from over here. The force is still acting this way. This is what I mean by extension cord, right? An extension cord just elongates the wire you have. Well, it's doing the same thing. It allows you to elongate where you're applying the force. that force is always going to be directed along the string. So since the string is acting horizontal, that force must be horizontal. All right, we'll see examples where maybe the string is acting up at some angle. Well, then the force would be acting up at that same angle. All right, so here I have kind of redrawn. Here's the person pulling the box with the string. This is how the force is acting. Here's that force, here's that arrow. It's along the same direction as the string. We call that uppercase T. Oh my gosh, again, this should be the letter O. Oh, this should be the word or F sub T. The only other thing I want to say about tension is it's often convenient to use strings and cables to change the direction of a force. And here's what I mean. Let's say I have this box that's kind of dangling. Okay, it's above the floor. You could support this object several ways. You could maybe just hold it, right? You could hold it from down here, and you'd be applying an upward force. You could hold the string from right here. Maybe you have your fist right here, and then it'd be supported upwards from this tension. Or you could have that rope going over a pulley. You can't really see the string here, but it's going along like this. Okay. And now if you want to support the block, you'd be tugging downwards on it. So just by using a string, you could change whether you're applying a force upward from the bottom, upward from the top, or you could be tugging downward. And they're all doing the same thing. They're keeping that box supported. Okay, there's the tension force. There's only one more thing, a part 4, and to be honest, I don't even know if you have to write it down. I just want to emphasize, don't get yourself boxed in thinking you have to use either tension or normal force or weight. It's very possible you want to label and you have forces that don't fit the label for these things we've written down. For example, here we have a girl pushing a box. Well, that's not really tension. If we're thinking of the force that the girl is pushing, that's not really the normal force. It's certainly not weight. You can come up with your own names. Maybe you call this the pushing force. Okay, or maybe you label that F sub P. All right. As long as you clearly label things. Here, as I have a stoplight hanging from some wire, you probably wouldn't want to call all of these tensions, because to be honest, these strings might be exerting different forces. So maybe you call them T1, T2, and T3. Or maybe you're like, oh, this is force left, this is force right, this is force middle. That's all okay. Just make sure you have them labeled. Okay, don't think you can only use the ones that we have named. All right, that's all I got for this video, defining Newton's second law and going over some of the common forces. Thanks for watching.